Good morning. Today we have a small proof to do. We're going to use integration by parts to prove that the integral right here of x squared plus a squared in parentheses raised to the n power dx is equal to this part right here. So that's what we're going to be proving today. The reason why I chose this specific example is because in order to do this proof, we're gonna have to use like small tricks and methods, little techniques that are gonna be seen a lot through integration by parts problems. So just normal problems involving integration by parts, we're gonna be using that. So if you can do this integral, you should be like pretty solid and good to go when doing integration by parts. So let's go ahead and get started with this one. So solution, and we are going to use by parts. So if you're watching this, I'm going to assume you guys are already very familiar with by parts or have a good like grasp on the basics of by parts and know how to do this. So we're not going to go too deep into by parts because this video is not too focused on that. This video is more on proving this, right? And if you guys are not focused on, if not, you guys are not that good at by parts, I mean, you can probably still watch it and maybe learn a thing or two on by parts. But if you're not good at all or don't know anything of integration by parts, then I suggest you review and get yourself a little bit familiar before attempting this. And but if you have a good understanding of this, a good basic understanding of integration by parts, then this video will be good to learn some new techniques or practice some new techniques to apply to your problem solving. So yeah, let's go ahead and prove this. So we have the by parts formula. I'm going to assume you guys are good with that. So the integral that we're going to be working with is just going to be this. So the integral of x squared plus a squared all to the nth power dx. So we're only going to use that. This is going to come later. We're going to use this. Okay. So let's go ahead and rewrite this as, this is a trick that you're obviously going to see later on in solving these types of problems, but we're going to learn it right now. So rewrite it as this. So this here is equal to this integral here, which we're basically just multiplying 1. So 1 times x squared plus a squared all over all to the n power dx. So you can rewrite it like that. And let's go ahead and choose our u. So we're going to go ahead and let u equal to x squared plus a squared to the nth power. So we're going to let u equal to this. And just choose a u that is good to differentiate. But when we choose our dv, if you guys forgot, choose your dv as something that's good to integrate, right? So in this case, we're going to choose our dv to equal 1. And the integral, basically, this basically is just telling us that dv equals dx, right? dv equals dx, right? If you don't know, it's just because we're just, this is basically just, that's basically just our dv1 multiplied by dx. So choose your dv as that, all right? And that's just because 1 dx is easy to integrate. So if we choose our dv to equal to 1 times dx, which is this, if we choose that, then that means our v, we take the integral of 1, which is just going to be x. So you want to choose something that's easy to integrate. And yeah, so yeah, that means that we have to find the derivative. Now we're going to have to find the derivative of this because we chose u to be x squared plus a squared to the n power. So that means we're going to have to find the derivative. So that's d over dx of x squared plus a squared n. And I'm going to save some time here. This just involves a chain rule. You guys should know how to do this. If not, then just go ahead and review that. But chain rule, yeah. So that's going to be this. This is going to be your derivative. Just to save some time, I'm just going to give you the derivative right now. Okay, That's n minus 1, by the way. This is n minus 1 in case you can't read my writing. So that means that du is equal to this, the derivative again, 2xn times x squared plus a squared n minus 1, and just multiply your v, right, your dv, and that's just dx. So just remember, that's just v du, right? Just multiply by your dx. It's just by parts. We don't have to go too deep into that. Okay, so now that we have that, let's go ahead and basically rewrite our entire integral. I like to rewrite this entire integral just to see things a bit clearer, you know, just to know where we're at. So we're going to rewrite the entire integral now. So this is equal to the integral of x squared plus a squared to the n power dx, which is the integral right here, right? Just rewrite that. Is equal to, basically is equal to, just write this, but with the variables that we already found. So that is going to be that v, remember our v is x, it says right here vx. So v multiplied by your, what does your u, which is, you found your u, which is that. I don't want to take away too much time because I know this video is probably going to be like really long, but I'm going to try and explain it just for the sake of explaining it. So you guys can skip around if you guys already know this stuff, but I actually want to like explain this stuff because, okay, so we're going to subtract by our integral, which is basically just v multiplied by du. So v is x multiplied by du, which is this, right? So multiply by, just take out the 2n, right? Because it's they're constants. We don't have to keep them in the integral. I'm gonna, if you guys have any questions on where I'm getting these values, just ask me and I'll try and get back to you. But overall, I hope you guys are following along with this. Okay, so now we have this. Plugging everything we have here into the formula and rewriting the whole integral all over again. This is what you guys should have now. So now let's go ahead and continue. So we're gonna use some substitution right here. Notice how there's two variables, and it looks like we can use by parts again, but let's not do that. That's just gonna overcomplicate things. Let's go ahead and, yeah, I know that because I tried, when I first saw this integral, I tried doing it by parts, and I was like, yep, that's not going to work. So let's go ahead and do some substitution. Or maybe it is going to work. I did not go too far into it because it was getting way too complicated. But I found out that substitution works out a bit better for this one. Did I spell that right? I don't know. Doesn't matter. Okay, so we're going to use some substitution. So, yeah, I did not spell that right. Substitution. Okay, so we're gonna go ahead and use some substitution. So let's go ahead and take the integral that we have here, which is x squared, just to see things a bit more clear. That's what I like to do. You guys can do it without rewriting the integral. Go ahead and do it. So this is going to be our integral. So we're going to this is going to be a u substitution. This is not by parts, by the way. This is going to be a u substitution. So it's going to be a little bit of a different, this is a different, we're going to separate that, right? This integral is separate from the one we did here. So let's just use a u substitution. So this is not by parts. Actually, no, let's not use a u substitution. Let's use a q substitution. So we're not going to, just to keep things a bit more neat and organized, we're going to use q instead of u. So let q equal to x squared plus a squared. So we're going to let q equal to whatever's inside this parentheses. And that means, let's go ahead and solve for x squared, right? So if you solve for x squared from here, what will that give you? That's going to equal to a squared minus q. That should give you the... Actually, no, that's not what it's going to give you. Sorry about that. That's going to give you q minus a squared, right? So when you solve for x squared here, that's going to be q minus a squared. That's what it should give you to. But what did we say q was equal to? We said q was equal to that, right? So that means in reality x squared is equal to q, which is x squared plus a squared minus a squared, right? So that's a little trick that we're going to use, substitution trick. So this should check out, right? Because we defined q as x squared plus a squared. And then we solve for x, but we're left with q here. And since we define q as this, then we can plug that thing back in. So again, we're writing the whole thing again. That's going to be equal to the integral of x squared plus a squared. Because remember, x squared is equal to that. So go ahead and substitute your x squared minus a squared. And we're going to multiply that by this. So we're just substituting the x squared, which is that, into our integral. So that's all we're doing in case you guys are lost. So that's all we're going to do, right? And then after that, you know what we're going to do now. We're going to rewrite the whole thing all over again, but this time with the variables that we just found, because I feel like that looks a bit cleaner and easier to see in case we have to do some algebraic manipulation, which we will, and you guys will see later on. So the integral, we're going to rewrite the whole thing again from the top. So the integral of x squared plus a squared to the nth power dx. Let's write small since it's going to be a little big, a little long. So that's x. So remember, we're just rewriting the whole thing, right? We're writing this whole thing plus what we found out, right? With this integral right there, all right? Let's go ahead and do that. Okay, so x squared plus a squared to the nth power minus, all right? Now we got the 2n, and now we got the integral that we found out, right? Which is going to be the integral of x squared plus a squared n. So dx minus a squared x squared plus a squared n minus 1 dx. Okay, so if you guys don't know where I got this from, I basically just use a whole distributive property to distribute. I just multiplied this and put it here. This is just this multiplied, right? So just go ahead and use a distributive property to get this, and then just go ahead and put it into your guys's your formula. I'm just gonna go ahead and check my work, see if it's good. If we're good here, and so far this looks good. Okay, so we did good. So now we're gonna go ahead and distribute the 2n to your two integrals that we have here. So go ahead and distribute it. Again, you use a distributive property. So again, I'm sorry, we're gonna have to rewrite this unless you guys can do it like without it, but I like to rewrite things. So go ahead and skip this part if this is too long. So that's x squared plus a squared n dx. I just like being like detailed with this stuff just to really show where this is going, like coming from, you know. But if you guys don't want to see this, go ahead and skip, because I admit this is pretty long, but it's good to be detailed in your guys' work. Okay, so now we use a distributive property. Now we can go ahead and do our little bit of algebraic manipulation. This is again another trick that you guys, or not really trick, but a technique that you guys will see in like regular by parts problems. And that involves basically just notice what we have here. We have this one here, and we have this one here. And look at them, they're practically almost the same except for this 2n. So since they're practically the same, that means we can move one of these to this side, right? Let's go ahead and do that. So that means we're going to add 2n, the integral of x squared plus a squared n dx. We're going to add that to this side. This is why I like writing the whole thing like that, the whole thing from the top. So that way I can do little manipulations like these. And I can like look back at my work and know where I got my things. But that's just me. You guys can do what works for you. So that means that this goes to 0. So we completely got rid of that. So that means that now we have this. So you got 2n multiplied by the integral of x squared plus a squared over n dx added to this one right here, which is going to be x squared plus a squared dx, and that is going to be equal to that's going to be equal to, again, your x multiplied by x squared plus a squared n added by what you have here, so that's 2 and a squared. Yeah, actually, let's write it like this. It's not different, it's just this is the way the proof is, so I'm gonna write it that way. Not too different from what we had. In fact, not different at all, because we're just, it's multiplication. It doesn't matter which order you multiply. All right, so now that we have that, now that we have that, hold on, let me check my work, see if everything is okay. So far, everything does look okay. Okay, now we can use, look at this. We have this integral, and we have that integral, right? Let's factor out that integral. So if we factor this out, this is just factoring. You guys should know factoring, right? That's algebra. So if we factor that out, that means that we have the integral of x squared plus a squared to the nth power dx. We multiply that by 2n plus 1. Because if we use a distributive property, we're going to get this back. So that's just factoring. So we're good with that. So again, just sorry about that, but we're gonna do this again. This is just my style. I like to rewrite everything just to see where everything's coming from. That's just me. Okay, so now that we got that, we're good with that, right? So now let's go ahead and divide the whole thing, all of this, by 2n plus 1, just to get rid of this. So that cancels out. You guys should know this. This is good. This is just algebra, so we should be good with this. So okay, so that means that the integral of x squared plus a squared over n dx is equal to x, dividing the whole thing by that, x times x squared plus a squared to the nth power divided by 2n plus 1 plus 2a squared n 2n plus 1 multiplied by the integral of x squared plus a squared n minus 1 dx. Let's see if this matches. Yeah, it looks pretty good to me. So that is it. We're good with this. This is how we prove that integral. We use a bunch of tricks and some little manipulations that you guys, if you guys know how to use these tricks and manipulations, you guys should be pretty much solid with integration by parts. So that is it for this video right now. We're good with this. Any questions, anything you got stuck on, let me know, and I'll try my best to clarify things. And that is pretty much it. Hope you guys learned something new. Hope you guys got clarified with something. And yeah, that's it.